In this lecture, we want to learn how many motions are possible for a rigid body and how the kinematic joints can limit those motions and decrease the degrees of freedom in a system of multiple rigid bodies. We will also get familiar with the Revolute joint, which is one of the most common types of joints used in mechanical systems. Finally, we will have a couple of examples which will lead to derive a simple formulation to determine the degrees of freedom in a system. Let's start with the degrees of freedom for a free rigid body. In a three-dimensional space, a rigid body has 6 degrees of freedom because there are 3 possible translations along x, y, and z directions, and 3 possible rotations around x, y, and z axis. But in a two-dimensional plane, a rigid body already loses 3 possible motions because it cannot exit the plane. If we limit the motion in the x-y plane, a rigid body can only move along x and y directions and rotate around z-axis. So it will have 3 degrees of freedom: x, y, and theta. Moving along z direction and the other 2 rotations are not allowed, since they make the rigid body out of the plane. If we have a rigid body like this, it brings 3 degrees of freedom to our system. If we have more rigid bodies like a second, third, and fourth one, each of them add 3 degrees of freedom to the system. So the degrees of freedom for a system of multiple rigid bodies is 3 times the number of those bodies, because every rigid body brings 3 degrees of freedom to the system. Let's talk about kinematic joints and see how they constrain the motion. One of the very common types of joints is the Revolute joint. It is also known as a pin connection or a hinge joint. Let's assume that we have 2 rigid bodies like this one and this one. Generally, these 2 bodies have 3 degrees of freedom with respect to each other, meaning that either of them can move relative to the other one in 3 possible ways: 2 translations and 1 rotation. When 2 bodies are connected by a Revolute joint, it means that one point of one body should be always coincident on a point of the other body. Like this. I draw the 2 bodies again, this one and this one, and a Revolute joint between them. This way, the 2 bodies will lose the 2 translational degrees of freedom between them, and the only remaining possible motion between them is the rotation. So we learned that a Revolute joint takes 2 translational degrees of freedom and permits only 1 rotation between the 2 bodies. It can be defined between 2 rigid bodies, as you see in these figures, or 1 rigid body and the ground, like these examples. That's also the case for any kinematic joint. Let's have some examples to clarify how a Revolute joint can constrain the motions and decrease the degrees of freedom in a system. In this example, we use a simple approach to determine the degrees of freedom. The rigid bodies come to the system one by one, and each of them brings 3 degrees of freedom. Then, with adding the Revolute joints, the motions of those rigid bodies are constrained, resulting in decreasing the degrees of freedom for the system. Let's start. The first rigid body comes. it brings 3 degrees of freedom. If we add a pin connection with the ground, we will lose 2 degrees of freedom. So the degrees of freedom is now 1, which is this rotation here. Then a new rigid body comes and brings 3 degrees of freedom. With this new revolute joint between the two bodies, we will again lose 2 degrees of freedom. So the degrees of freedom is now 2, which is this rotation and also this one. It's not always that clear, by the way. At this point, if we pin this new body to the ground, we will lose 2 more degrees and the degrees of freedom becomes 0. Let's have a definition here. If the degrees of freedom for a system is 0, it is called a structure, just for you to know. Now I remove this last support and continue adding some more bodies and joints just to practice. I add this new body which brings 3 degrees of freedom. Then this pin here will take 2 degrees. Now I have a system with 3 degrees of freedom, which are these 3 rotations. This one, and this one. I add the final link which generates 3 more degrees. With a pin here, I will lose 2 of them. Now the degrees of freedom is 4 rotations. 1, 2, 3, 4. Let's have a definition here. This is called an open chain of links. The chain is open because it has started from the ground, but it hasn't yet returned back to the ground. Usually in an open chain, the degrees of freedom can be clearly seen, like this example up to this point. Now with this last support here, I will lose 2 more, and the degrees of freedom is now 2, which cannot be clearly seen anymore. Let's have our last definition here. This is called a closed chain of links. The chain is closed because it has started from the ground, and then after some links, it has returned back to the ground. And usually in a closed chain, the degrees of freedom cannot be obviously distinguished, like this example at the end. Finally, we can derive a simple formulation and say that the degrees of freedom in this system is 3 times the number of bodies, just because each body brings 3 possible motions, minus 2 times the number of revolute joints, because every revolute joint takes 2 degrees of freedom. Let's try this formulation for our example. The number of bodies is 4. 1, 2, 3, 4. The number of revolute joints is 5. 1, 2, 3, 4, 5. So substituting in the formulation, 3 times 4 minus 2 times 5 is 12 minus 10 becomes 2, which is the same result. Before I finish this lecture, let's try to apply the formulation we just derived to determine the mobility of another system. Mobility is the other name for the degrees of freedom, by the way. This is the schematic diagram of a drafting machine. Anyway, the formulation says the mobility or degrees of freedom is 3 times the number of bodies minus 2 times the number of revolute joints. Let's count the number of bodies. 1, 2, 3, 4, 5, 6. The number of rigid bodies, 6. The number of revolute joints, 1, 2, 3, 4, 5, 6, 7, 8. Number of revolute joints, 8. So 3 times 6 minus 2 times 8, the degrees of freedom is 2. In this machine, the end link can only translate along x and y directions with no rotation. Okay, I hope you have understood the revolute joint and the way it affects the degrees of freedom in a system. In the next lecture, we will talk about another common type of joints, which is the prismatic joint.